So this afternoon we're going to extend what we've been doing this morning by perhaps raising new project ideas, this idea of extending the exoclock focus into new areas. But we're also going to help the perhaps the beginners understand about the processing of basic transit data. And then later on in the afternoon, after a tea break, I'm going to give a short presentation on, well, it's advertised as observing with robotic telescopes. And then we'll have a final question and answer session currently scheduled for 4 o'clock this afternoon. So first of all, star of stage, screen, i.e. the computer screen, and exoclock. We have Martin Crowe, who is going to take us through Explore Part 2. Over to you, Martin.
Okay, thank you. I'll just share my screen. You'll see that?
Yes, that's good.
Okay. Okay, so as Rodney said, this is oops, I'll just start my timer. This is sort of aimed at people who are wanting to get into observing exoplanets. And so I'm preaching to the converted if you're already doing it. Hang on a second. My oh, that's a bit slow, isn't it? I don't know why it's doing that. Okay, so I've put things I'm going to quickly look at are what equipment do you need? Astro Image J, a very brief part about it. I know Richard Lee's talking about it later, but this is just how I use it for getting set up. The main part's about the introduction into HOPS, how to get the software, run your observations through it and upload to the Exoclock website. A tiddly bit about synchronous observations and a small mention about the possibility of data mining your own images. Okay, so what do I need? You're going to need some kit, obviously. If you're an imager and you're wanting to do science, getting into the science side of things, you'll already have this gear. It's standard for imagers, really. And likewise, if you're already doing photometry, you're going to have this kit. But you need a telescope, sort of minimum 150, although as Anastasia said this morning, you can go smaller depending on certain targets, if they're particularly bright or they've got very deep transits. Camera-wise, a CCD or CMOS, it's increasingly CMOS it seems these days, preferably a mono. If it's a colour camera, you can still use it, but clearly you can't put filters on that. So mono is much better. Accurate polar alignment is sort of essential, really, because they're long duration sets of observations, and you'll see later why it's so important. And a filter wheel is also useful. I mean, you could screw a filter straight onto the camera, but to have a selection of filters is handy. I would also suggest, though it's not essential, is having a permanent setup. You know, if you've got to set that gear up and get it all running, polar aligned and everything, and then put it all away again, and all the weather changes on you, to be fair, I wouldn't do it. It would just drive me nuts. Having a permanent setup, you can just go and get to it. And there's a selection here of observatories from the Crayford members. So this, the one on the left, can you see my mouse? Anyone?
Yes.
Yeah, okay. The one on the left is mine. It's got a warm room and a domed enclosure. I can control it from in there or indoors. The top one is Keith Rickard's, his metal garden shed that he's modified to have a slide-off roof, which works quite nicely, and he can control that from indoors. And the bottom one, which is quite innovative, is Simon Dawes' two sheds observatory, where you've got a small shed and a larger shed, and the bigger part, the bigger shed top rolls over the smaller shed, and the smaller shed's the warm room. It's very clever. So getting started, so you'll need to go to the Exoclock website. and you'll find information on there how to get started, get registered, and it will give you links to information and the software. So one of the links is this one, which will give you guidance on how to correctly observe. And we'll talk about one or two things to do with that as we go along. It's also got sample sets of data so that you can actually go and practice on hops without actually having done any observing. And that's probably quite useful for some people who are like itching to have a go. And certainly with the weather as it stands at the moment, it's not been that great really lately. And so you can actually get hold of this data, download it, and play around with it. And also the actual software itself, hops, the purpose-written software for the project, gives you guidance on how to upload it onto your system. It's a Python-based bit of software. It's very good. It's been improving all the time, and it is very easy to use. Doing the observations, so some things you need to think about: accurate computer clock. You can't rely on the computer clock in your computer to be right. You need something like Dimension 4, or there's lots of other stuff out there that you can use. I use Dimension 4. Ideally, a photometric filter, and so the preferred one is a Cousins R. You can use all different types of photometric filter, and indeed you can get away with a red filter, or even no filter at all. But ideally, photometric filters are beneficial. Arriving at the correct exposure for your target. Now, if you've been an imager and coming into this to do some photometry, clearly the brightness of your stars hasn't really been a thing that you've been worrying about. You're after faint detail and what have you. But for photometry, it's crucial that your stars are of a value there's no pixels in the stars that are saturated or in the non-linear range of your camera's response. And so you're going to need some software that can allow you to measure the pixel values in the images, the star images that you're interested in. Astro Image J is what I use. It's free. That's why I use it probably. But it's very good software. It can be quite, it's quite a learning curve, but for what I'm going to show you in a minute, it's quite straightforward. And if you Google it, you'll find it quite easily. And that's, as someone said earlier, it will run on Linux, Windows, or Mac operating systems. Okay, so you're all set up, and you've taken a test image of the field of view where your target is, and you want to see how your stars are exposed. When you open AIJ, you get this ribbon with the tools on it, and you open the file in the normal way and go to where you saved your test image. When you scroll your mouse over the image, you don't get a pointer, you get a concentric measuring circles. And as you scroll over the image, you'll see up here, there's some values. These will change depending where you are on the image because it measures underneath that circle. And the one that you're interested in is the peak value. And if you settle it over the target star, which is quasar 5 in this particular instance, and this is it, you can see that the peak value is 15,500. Okay, generally speaking, you want to be no more than sort of between 30, 35,000, depends on your camera. But that's sort of what you're looking at. So here you might sort of think, well, actually, I might need to go longer so I can increase my signal. If you alt-click on the star, it will bring up a profile of that star where it will give you the same information about the brightness. As you can see, the top pixel there is just under 16,000, but it also gives you your full width half maximum. And I know with my system that if it's showing 4 pixels, I know my image is reasonably sharp, and I don't want that. If you're doing photometry, you don't want sharp images. You want them to be slightly defocused. There's a couple of reasons for that. One is if it's sharp, the maximum pixel value can vary widely between images. And so if you've got it all set up and you're sort of perhaps in the sort of 32,000 range, it's quite possible in the next image you do, or subsequently, it'll pop up into the 40s, and because you're in trouble then, because you've gone into the non-linear range. So by defocusing, you soften that out. It stops that large variation. And the other advantage is, because the starlight's spread over more pixels, you've got less brightness per pixel, and therefore you can increase your exposure to increase your signal to noise, which is obviously beneficial for measuring. And finally, you can also shift click on the target star, and it will bring it up in a tabulated form with other information. But you can see in here, you've still got your full width half maximum value and your peak value, but your source signal to noise is quite useful to see just how, where you are with that. Okay, so you've used that to do test images to get to the exposure that you want, and you've sorted your focus out. You've done your images, you've done your transit, and now you want to process them. And so you've uploaded hops onto your system, and you click the execute file, and a window like this will pop up with the code running by as it loads itself. And once it's done its business, you'll have this front end window come up. You will still see in the background that code window, so you can always have a look at that if you need to. This is the sequence it's going to go through, and the first thing you do is select your data and target. So you click on that, and you get this window where you can choose the directory where you saved your image files of the target star, and you also need to put in there your calibration files, and they need to be named with bias, dark or flat, so that hops can identify them for what they are. It won't automatically see your image files, your light files. You'll need to put a filter in there, and because this was quartile 5, I've put Q in there because that's in the title of the star of the file, and it will automatically see them. There's a few key header words that it will want to see in your FITS header, which it should normally do, and you will need to tell it what the timestamp is on your images, whether it's the mid-exposure or the start of the exposure. Next, you'll choose your target. You click this, and you can type in the star name, so quartile 5, or you can put the coordinates in. If you're on an internet connection, it'll once you put the name in, it will find the rest for you. These ones here, your name, observatory, and what have you, they're already pre-populated because that's what you've put in when you install the software. And then you need to select your filter. Once you've done all that, you can click the save options and proceed, and it will take you to the reduction window. And this is where it produces masters from your calibration files. And then once it's done that, it will start calibrating your images. It's a good idea to check this show all frames box, because when it's running through the calibration, it will show you which frames being done at the time. And sometimes things can go amiss. It will stop for some reason, but you can look back in the code and you can see that there's some error or something. If that happens, you're going to have to go in and you might have to remove that particular image. And I would suggest that it wouldn't be just, in this instance, 215. You'd want to have a look at 216, because it might be as it's loading that it's had the problem. From there, it runs onto the alignment window, which is pretty sort of normal. It looks at the stars in the image, decides which ones it's going to use, and then in the code you can see that it's running through aligning them. And again, if there's a problem, you'll see it here, and give you a chance to go back in and change it. If it does stop for any reason, you will always have to go back to start again and do it. So the next window is the inspection window. So this is the step before you're doing the photometry, and we've got a window here that shows your one of your images. Over here, there are two plots. One is the sky brightness measured against the time in hours, and that's through your observation. Hang on, I just want to get rid of that. That's it. And each one of these dots is the sky brightness measurement from each of your images. Okay, and down here, likewise, this the PSF, which is basically a focus to see how good that has been through the night. If you double click on one of the dots, it will bring that image up, and it will put a little red arrow against it there and there in both windows. And so this is the first frame, 001. If you want to inspect these other images, you can double click on it, and you will see the image come up. And clearly, there was a bit of a wobble in the tracking. So if you right double click, it will turn the black dot red, and all the red dots are ignored by the software. If you want to reintroduce it, you think, oh, it's actually okay, you can right double click again, and it will turn it black, and it will be reintroduced. Looking at this this plot, it's quite obvious that the sky was not perfect at the beginning of the observations. There was some high thin cirrus or something going through, but it cleared afterwards, and it went to this more normal, what you want to see, sort of line. And normally through the night, it would sort of run down and then back up again with brightness. So you can go through manually and select the stars you want to keep in and take out. But another way of you might want to sort of take a block out is to use the thresholds. So if we go to the sky threshold, so I've set this at 4.3. Anything above 4.3, it will remove. It's clipped a couple at this end, and you can re-include those if you want by right double clicking them. And likewise with the PSF, you can set that to a value, put that at 6, and again anything above that's removed. These are variable. You can, particularly this one, you might do your photometry and then decide to go back in and lower that to say 5 and see how it affects your results, because obviously there's a bit of noise going on. From there, we proceed to the photometry window. Now, when this window first opens up, you'll have your star image, but there won't be any stars selected in it. But the red box will be there, and the red box indicates the field of view that is in all of your images. Okay. Now, this is where your polar alignment is important, because if polar alignment is poor, you might find that your red box is like down here in one of the corners. And so you've excluded a whole bunch of sky where there's potential check stars. So polar alignment is what you want. Now, what next? Okay, so you're going to select your target. So you need to know in this image where your target is. You can zoom in using your roller mouse, the little wheelie thing on the mouse. I don't know what it's called. And double click on your target, and it will put a red measuring circle around it. It'll also put some information in up here, position and the pixel counts. It also gives you the radius of the circle, which you can vary if you need to. Now, sometimes it's necessary. You might find that when you've done your photometry, you might need to make it a little bit larger or a little bit smaller, and you just try it. It's just one of those variables that allows you to fiddle with your data a little bit. Also, if you get a blended star, that is to say, there's another star that's right in contact with it or overlapping, you might actually have to increase the radius of this so that it encompasses both stars before you can do a satisfactory measurement, and just hope that that other star isn't a variable. Okay, so you've got to choose comparison stars so that this can be measured. And up at the top here, which is probably, I don't know if it's blanked out in yours, it's behind some of Zoom stuff for me, but it gives you an idea of things to think about. So the comparisons ideally want to be close to your target. Good luck with that, because they'll be where they'll be, but it's, you know, clearly if they're closer the better. But if you've got good flats, you shouldn't have too much of a problem. Be of a similar magnitude, and hops will help you with that, and I'll describe that in a minute. Of a similar color can help, but again, hops doesn't help you with that, so you'll have to look that up yourself. You don't always have to do that, but you can get second order extinction when you're going through different from low altitude to higher altitude in your observations, and they need to be stable, not variable stars. Okay, so to help select stars of a similar brightness, there's a little drop down here, and if you want to start at 10%, this is the percentage difference in brightness that it will select. So all of these stars that it's selected in this image are all within 10% plus or minus of the target star. Now, in some images, you'll have nothing. There'll be nothing there within 10%, and so you'll just work through the percentages until you get some that you can use potentially. And if I put that on 40%, you can see you've got loads to choose from. But the ones I've actually picked are the 10% ones. You can see if I just run them backwards and forwards. Now, down here, there's a couple of things that you can that can help slightly. If you've had a very that the evening wasn't that great, the atmosphere was a bit wobbly, and so the PSF of your image has been changing. If you tick this box, it will allow this radius to alter proportionally to the PSF of that image. And if your stars are a bit oval, you might try this where you can align the aperture with the geometric sensor rather than the brightest part of the star image, to stop the measuring circle clipping off part of the star. Okay, right, so you're all set up, so you're going to run the photometry. You'll go to this next window. This won't be populated yet, these ones here, but these will. You'll see your star, and it'll be wobbling around as each image is opened and they're measured. And as they're measured, these dots will start to appear. And you've got one dot represents the PSF of the image, and the other is the aperture. And they need to be reasonably coincident, not sort of spread out all over the place. And you can see that the three comparison stars we've got are nice and flat. They're not varying, which is what we want. And when it's finished, it will come up with a little window which will tell you where the photometry results are stored, with photometry 3 in this instance, because I'd already done two other sets of measurements. Now, if, for instance, C3 was actually varying, so you could see that it was clearly not stable, it was doing something, you can take it out of your calculation by just deactivating the checkbox, and then the ones above it will readjust themselves with that taken out, and it will then give you it will then be telling you it's saved in. It'll be photometry 4, will be the next one. Every time you do photometry, it creates a new folder for that photometry, and you'll see that in a bit later. From here, we go to the fitting menu. Now, again, when you go into here, there won't be anything showing here. You have to go to the drop-down menu and select your file. So we're selecting the first one, and then this will pop up. It's showing your data points of the transit. It shows the blue line, which represents the expected transit light curve, where they're expecting to see it, and the red line is the best fit to your data. Now, bear in mind that the whole point of the exercise is measuring the difference from left to right of the coincidence of the red line and the blue line, because that's giving us the observed minus calculated value that they're after, which is the center value they're after. But in this instance, they're quite coincident, and it's about -2, so it's come a little bit early according to this particular set of data. Sometimes you'll find that the blue and the red lines, the depth of the transit, the RP over RS, as it's called, don't line up very well, and they can be out. That's indicating that there's something wrong with your measurements. You need to go back and perhaps look at the photometry. This is where the color of the stars can be important, and can have an effect on that. Okay, now there is another fitting that you can do, but personally I never do this these days. I just go straight to the website and do it. So this is the Exoplanet homepage. The thing you're interested in is, and I don't know if you can see it, but up the top there, there is My Lab, and you're after upload observations. This form will appear, which you just need to go through and fill out. So you need to tell it what telescope you're using, and you'll have put your what telescope or what your equipment is when you first register, and you might have more than one telescope, so you need to tell it which one you were using for those observations. You then need to go and choose your file that you're going to upload, and so in here you can see that the folder where all your calibration files were and your observation files, HOPS puts a photometry file in for each set of photometry that you do. So we're going to look at photometry, and so within that folder there's all this stuff that it puts in, but the one that you're really interested in is photometry aperture. This is the one you're going to upload. We've scrolled down the page a little bit now, and you go and select your target from the drop down. It needs to be JD, they do the transformations. What your timestamp is, whether it's the start or the middle. This will be, for how we're doing it, this will always be on flux. What filter you're using, and how long your exposures were, 120 seconds in this particular instance. You then need to select the detrending method that it's going to apply when it analyzes your file. You've got air mass, there's quadratic, and there is also linear, and you need to try all of them. It's no good just doing one and going, oh, it's all right. You need to try all of them and see how it affects your results. The first fit that you saw in HOPS is a quadratic. Okay, so it should get, so doing the quadratic in here should give you similar results. Not always, but it should do. Any collaboration, so if other observers were with you when you were actually doing the thing, they should be in there. And comments, and the comments that relate to the observations themselves. So what were the weather conditions like? So in mine just then there was light cloud or thin high cloud for the first couple of hours, or if there was blended stars or any instrument issues, like I had a power cut and then I had to restart it, or stuff like that could affect your observations. You click upload, and you'll get a window like this. This is it will be the same as this, except there'll be 3 buttons here. This window is actually the final window once you've uploaded, but it looks exactly the same. It gives you your results. So the RP over RS, which is the depth of the transit and how it compares with the literature, and in this instance it was very good. The OC minus the O minus C, which was -2 minutes plus or minus the uncertainty. The quality check, this is really useful, and this is based on how well your instrument has performed in the past. So the more observations you do, the better this becomes, and it can affect the stars that you're given to actually observe, because if you're it's performing better than an instrument of that particular size, because of, you know, you've got better skies, or conditions are generally better, you'll get fainter objects or more fainter objects to observe, and vice versa, of course. And it's also handy when you're having trouble with a set of observations, because things might look like they should be okay, but when you look at the residuals and you know it's saying, oh, you know, it should be about, we're expecting about 4.3 or whatever, and then you look and it's sort of 6, it's like, yeah, okay, so things weren't quite as good as I potentially thought they were. You've got some diagnostics here to help you as well. These all want to be blue. If any of them are green, it means it's very borderline, and you need to definitely go back in and sort of see if you can improve your results. And if they're red, then that really isn't good. And if you can't improve that, then the observations won't be of use. And that's always a disappointment. It does happen. You know, it's just one of those things that the night doesn't always work in your favour, especially with our maritime weather that we have. So diagnostics, it's giving you the signal to noise. They're looking for more than 5 for the signal to noise for the transit. This is a particularly good signal. The RP over R is how it compares with the literature, the depth of the transit, and this was good. Are there any systematics? That was good. There wasn't, the systematics didn't look bad, even though that weather was not quite right at the beginning, and the few or no outliers. This, actually, I'm going to look at this graph here, but I'm going to go through here. Here we go. So I always save these images to my observations when it's done. This was a linear trend that I uploaded, and in a perfect world, this line would be horizontal. That's good. You don't want, if it's really steep, that's not good. There's systematics affecting your observations, and likewise a curve to the line. So it's an indicator of, again, how good the observations are, basically, and the conditions at that time. This isn't too bad, as you know, this is quite reasonably normal. It'll also give you a plot of your observation against all the other observations up to date for that target. And this one's quite interesting because there's a bit of a spread here. So, you know, I don't know why that is. These might be wrong. These might be wrong. Of course, you know, with my data being there, I'd like to think that it's right, but you never know. More observations will sort of clear that up. So that's pretty much it for hops. So I'm just going to talk a little bit about synchronous observations. Now, as mentioned, the Exoclock software has a schedule. So when you register, it will give you a schedule based on the instrument you've got. And then over time, how well that instrument's performing, it will give you observations or targets to go for. Now, there are targets that although you could detect the transits, the detection would be very weak, and subsequently the results would not be useful for the project. But it was realized that if you combined the observations from small telescopes for these types of target, your results could be actually very good. And in fact, this was the first, I think this was the first one we did. There was 11 observers. I think there was 13 total observations, because they were done over more than one night. There was 2 nights of observations that went into this. And there was a range of scopes used from 8-inch to 12-inch. And the results were equivalent to using a 44-inch telescope. And I think they said they was as good as the test observations. I think that's what I heard. It wasn't a particularly faint target. It was 11th magnitude. so sort of borderline, and but quite a small transit depth of just under 5 millimags. And this was the result. And in fact, Anastasia also showed this, I think, this morning. And then finally, the possibility of data mining your own images. So you've just sat on a star for 5 hours or more, taking images and measured your target star. But of course, it's possible that within that same field of view, there are other variable stars which people are also interested in. Now, you can go onto the AAVSO website and create a chart for most stars. So if, say it was, I don't know if you can do it for Quasar 5 actually, but generally speaking, you can type the star name in and it will produce a chart for you, and you can ask it to include in the chart other variable stars. And of course, if they're conveniently placed, then you can measure them and then upload your results to the AAVSO or BAAVSS. What was I going to say? Oh yeah. Also on that chart, it will give you comparison stars, and so they can be useful to actually use in your exoclock measurements, because those stars have already been tested as being good for comparisons. So it's something to think about and try. HOPS can't help you with that. That's going to be something else, and you're likely to have to use something like ARJ and the BAA VSS spreadsheet to do your photometry. So that was that. I just thought I'd include this one. This was one of the check stars that I was trying to use with Kepler 41. I didn't know it was Kepler 451 at the time, but when I did the photometry, you could see that this was something really quite interesting. It was clearly varying, and I'd never seen a light curve quite like it. There's some transits here. This is not planetary transits. These are another star. It's a large blue star with another smaller companion. But it was very, very interesting, and they're whipping around. The time difference between these two transits is 3 hours. So quite interesting targets. Sometimes objects quite often sort of can turn up in the same field just by happen chance. This does actually have exoplanets around it, but they're not transiting. They've been detected by timing variations of the orbits of the two stars, I believe. So I've quite quickly gone through what equipment you need to do this type of work. I mentioned how I use ARJ to find the correct exposure and focus. I've done an introduction into HOPS, how to get the software, how you run your observations through it and upload your observations to Exoclock. I've briefly mentioned about the Synchronous observations group, where targets that were normally too faint for the telescopes, or the bulk of the telescopes that are being used on the project, can now actually be observed and produce really useful data, and also the possibility of data mining your own images. And so that's me done. I don't know, I think I had a couple of minutes left, didn't I? But
yeah, you've done very well. We got 5 minutes before the next presentation is due. There's a couple of questions coming up. The infamous Roger Dimmock asks, asks, interesting exit from Qatar 5B transit, moon or imagination?
Imagination.
The other one's more real. You mentioned increasing the aperture to embrace an adjacent star. Won't that mess up the transit depth curve?
I don't know. I'm sure I've done it once and it was okay. It depends on what the other star is and what it's doing, really. Normally, when you're looking through and seeing, oh, this one's not had many observations, that's why, because people have looked at it and thought, sod that.
Language, Timothy.
Not language. Yes, so clearly it could introduce some problems, but it's the nature of the beast, really.
Okay, there's a question from William Stewart. William, do you want to read out the question?
Yeah, sure. I've got a C11 which has got auto guiding on it as well. So is it beneficial to auto guide, or should one just rely on accurate polar alignment?
Sorry, that's one thing I didn't put in the slide. No, you'd be guiding as well.
Okay.
But even with mine, with the guiding, the polar alignment is just a smidge off. It's about as good as I can get it. And when you saw the red, can I go back? There we go. When you see the red box on mine somewhere, there it is. You can see there is a little bit that's lost, even though I've got guiding. But so yes, no, definitely you've got to use your guiding, because well, if I didn't use guiding, I would lose a lot of images because the tracking on its own is just not good enough. So
okay, that's clear. Thank you.
anyone else?
Just looking down the list. I think that's pretty much got everything. Kim is thanking you for a great presentation. He's been looking for a nice project to learn to use Python. This looks like the right one for me. Okay.
I would say that where I mentioned about the AA VSO charts, that is quite useful. If you can, if there is a chart that it will plot for you for a particular target that we're going to do, it will automatically give you the check stars that you could potentially use, and so you can compare those with the stars that Hops pulls out and try them. So it can help you, because they would have I don't know, it will give you the color of the stars as well, I think, on there, if I remember rightly.
Okay, I think the questions have dried up, Martin. Thank you very much for that. That was a whistle-stop tour through
It was quick, wasn't it?
AIJ and Hops in detail. So
Okay.
that should give
Simon
people...
has just come in with a question right at the end.
Is he? All right, sorry, didn't see
That's
it.
okay.
Yep.
He was asking, if you use Nina, it can show you the variables in your field using an... Actually, it's not a question, it's a statement to say...
Yeah, it was a statement, because someone mentioned about how you identify variable stars, and Hops doesn't do that. But if you're using Nina, sequencing software, then there is a plugin that will actually take one of your pictures and then annotate it with these are check stars and these are variable stars.
Wow.
That's really good.
I don't actually use that, as it happens, but it is there.
Why aren't you using it is the question.
Poor planning, because you have to spend a little bit of time before. It is part of the command that tells you what the optimal exposure time is for your exoplanet observation. And I tend not to use that because it takes about 10 minutes, and I'm never that well organized.
Okay, we're done.
The last question here from Kim. Do you usually fill up all 10 comps to hunt for new variables? Oh yes, the long list there. Yeah, the comparison styles. Yeah.
No, I don't actually. The idea of actually doing that just to look for variables is quite interesting. I've never thought of that. But no, I don't. I'm just concentrating on the exo transit to start with, and then later on, it just go back into the images. And but I'm only really looking for variables that are already known about. I'm not actually trying to discover any. It's just adding to the archives effectively, because other people are studying some of these styles or types of style, and it just adds to that knowledge.
Yeah. Okay, Martin, thank you very much. Well
Thank you.
done. Absolutely finished bang on time.